All right, good afternoon, guys. So I want to begin. Sorry, I'm running just a few minutes late. I got a message saying that you guys weren't able to see the homework, and that's definitely a problem. So I took a minute to remedy that. WebAssign has apparently been doing something a little bit funky, but it should be fixed now. And because you've lost a day and a half of time that you could be spending on that homework, I'm going to revise the due dates a little bit as well. So I want to start by talking about that. So here is the .cam. This is Calc 1, Section 4. Okay, so you should be able to find homework 6 now. And I changed the due date to next Friday. Which is the 18th. Wait, no, sorry, it's the 16th, right? But I want to encourage you to start working on it as soon as you can and to put as much time in as you can between now and Monday, because we are going to start covering more new material next week. I'll do something similar with next week's homework. It will open up on Monday, but rather than being due the following Monday, I'll probably give you until Wednesday. And that way we can kind of work our way back from the damage caused by this delay. So homework 6 covers the topics that we talked about last time, the chain rule and implicit differentiation. I want to talk more today about implicit differentiation and look at some of the cool things we can do with it that before we couldn't do. In particular, I want to attack the problem of the derivative of inverse trig functions and the derivative of the logarithm function. We're going to work more next week with the derivative of logarithms. Once we have those things handy, it'll be time to start talking about related rates. So that's kind of the outline today. We're going to do more implicit differentiation. Last time we introduced this and we saw that it's a consequence of the chain rule. But since we spent most of our time on Wednesday practicing with the chain rule, I wanted to get more practice with implicit differentiation. And then we're going to cook up derivatives of inverse trig functions. Now, I'm fully aware that the trigonometry classes here at Santa Fe are a little bit soft. They do not push as hard as they really need to in order to prepare you for calculus. So I'll spend a little bit of time reviewing the inverse trig functions before we actually cook up their derivatives. But first, a little bit more on implicit differentiation. So let's take a look at that. Before I get into examples, any questions about the issue that happened with the homework? Or the due dates? So if you're still not able to see the homework, please try to look right after class and let me know. If you're still not able to see the homework, that's a sign of something more serious than I was thinking going wrong on WebAssign, and I'll have to reach out to our WebAssign tech to see if there's something they can do to it. But it should be visible now. I'm pretty sure I fixed the problem. So if it's
the homework popped up for me today.
You can see it now. Okay, good. Good. So then we're ready to dig in. Remember, implicit differentiation is essentially using the chain rule to differentiate functions where you've got both x and y is understood to be the dependent variable, x is understood to be the independent variable. If you want to read more about this, there's something called the implicit function theorem, which describes what's really going on there. But the basic idea is that even, if you picture the graph of a circle, you know that that fails the vertical line test. So that's not a function, right? Y is not a function of x there. look locally, if you zoom in on any one part of the circle, as long as that one part passes the vertical line test, you can treat y as an implicit function of x there. So that's where the name comes from, but in practice, we just have to know how to cook up the derivatives. So a fun example would be to find, and I'll use the Leibniz notation here, since we practiced primarily with the prime notation last time. Find dy dx, where cos xy equals tangent of x. So the challenge here, of course, is that this is not an equation that's been solved for y. If it was solved for y, and we just had y equals a bunch of stuff involving x, then we could use all the rules that we have to differentiate and find dy dx, aka y prime. But here, it's much easier, because this is very hard to solve for y, to jump in and differentiate implicitly on both sides with respect for x, with respect to x. So on the left-hand side here, there's going to be a meaningful amount of chain rule and product rule work that we need to do. The right-hand side is a little bit easier to compute, so let's start with that. The derivative d dx of tangent x is secant squared of x. On the left, we first use the chain rule to kind of peel off this outermost layer. Remember, we work from the outside in. So the derivative of cosine is negative sine, and I leave the inside alone. But then I need to multiply by the derivative of the inside. So I'll write that as d dx of xy. And then when we take the derivative of x times y here, we're going to need the product rule. So we'll have negative sine of xy times. Within here, I use the product rule. So first I'll differentiate the x, that's a 1, leaving the y alone. And then I add that to what I get when I leave the x alone and I differentiate the y. The derivative of y, we could write as y prime, but since I'm using the Leibniz notation here, I'll write that as dy dx. They mean the exact same thing. And then my right-hand side is still secant squared of x. I'd like to pause here for a minute and take any questions.
So you just carry down the 1 from y and x?
So this is a product rule. So I differentiated the x and I left the y alone. That's like u prime times v. Plus, then I'll leave the x alone and differentiate the y. That's like u times v prime.
Oh, okay.
Do we see it? It's a little bit sneaky, but yeah, this is the result of applying the product rule to this. Now there's some extra steps that we need to do from here in order to find dy dx, because I've got all this other stuff going on. So from this step, you would think of this as like an algebra problem where your goal is now to solve for dy dx. So if I want to solve for dy dx, what would be a good first step? Think of dy dx as a variable that I want to solve for.
Divide both sides by negative sine xy.
Yeah. So if I divide both sides by negative sine of xy, then I'll get 1 times y, or just y, plus x times dy dx equals secant squared of x divided by negative sine of xy. Everybody comfy with that? So what would I do next?
Subtract y.
Good. That would give me x times dy dx equals, I'll write the negative out front here, negative secant squared x over sine xy minus y. And now my last step towards getting this by itself is going to be to divide both sides by x. So I'll have dy dx equals negative secant squared x over sine xy minus y, all divided by x. And remember, of course, these fractions are grouping symbols. It looks like this. And the denominator is x over 1. So if I wanted to, I could write this as negative secant squared x over the sine of xy minus y, all being multiplied by 1 over x. And if I needed to find a tangent line, I would plug in the x and y value at the point where I wanted to find the slope. If I wanted to find horizontal tangent lines, I would try to figure out where this is 0. That would be a little bit tough with this expression, but we could try. But this is the upshot, right? We are able to solve for dy dx after implicitly differentiating our expression. Any individual steps we'd like to look at more closely here?
Is the answer the final product on the right or the final product on the left?
So our final answer here would be this expression.
Oh, okay. Okay.
Yeah, this is dy dx.
I lost the order for a minute.
Oh, I see. Yeah. So we run down and then down. I'd like to do at least one more of these just to get a good feel for it before I move on. Are there any other questions on this guy? Okay, let's grab this next example from your homework. There we go. So we'll come back to the inverse trig stuff a little later. Let's do something involving the implicit differentiation, something a little bit tricky. Let's see. We can look at, well, let's see. None of those are really terribly tricky, are they? Yeah, because we meant this to be a gentle one. I'll let you guys pick. Between 16 and 17, what would you more like to see? You can let me know in chat there. Just type 16 if you want 16 or 17 if you want 17. Daniel wants 16, Becca wants 16. Okay, 16 it is. So that's x times e to the y equals x minus y. And we want to find dy dx, or y prime. So it's going to be the same sort of procedure. We're going to differentiate implicitly on both sides with respect to x. That'll give us an equation that we can solve for dy dx. Oops, sorry, camera focusing. There we go. So my first step is to apply the differential operator d dx to both sides. On the left-hand side here, I'm going to need the product rule because x times y is clearly a product. So that will be, first I differentiate the x, that's 1, and I leave the e to the y alone. Then I add to that the x left alone times the derivative of e to the y. E to the y differentiates to e to the y times y prime, or if we're using the Leibniz notation, times dy dx. So you can think of it as really just being like the chain rule, right? The derivative of e to some stuff is e to that stuff times the derivative of that stuff. And then on the right-hand side, this is a difference, x minus y, so I don't need any special rules. The derivative of x is just 1. The minus comes along, and the derivative of y is dy dx. And again, you could write this using the prime notation too, just instead of dy dx, writing y prime. Either way would be fine. And so now I've arrived at this place where I've got an equation that I can solve for dy dx. So this term has a dy dx in it, and this term has a dy dx. So I should push both of those to the same side. And then anything that doesn't have a dy dx in it, like this and this, should go to the other side. So I will have x e to the y times dy dx plus dy dx equals 1 minus e to the y. So I subtracted this term over here, and I added this term over here. Now that every term on the left-hand side has a dy dx in it, I can factor dy dx out. That'll give me x times e to the y plus 1 times dy dx equals 1 minus e to the y. We need to factor this out so that we can then divide over by this piece and get dy dx on its own. So my last step is going to look like dy dx equals this, 1 minus e to the y, divided by this, x e to the y plus 1. And that's it. So these problems, they're not too bad. There's nothing too frightening here or too overwhelming as long as you're patient. Any questions about where any of these pieces came from or what we're doing with them? Okay. So then, the next thing I'd like to do is spend a little bit of time reviewing the inverse trig functions. Make sure we remember what these are and how they work. Now there is a link in your modules under the review material section that takes you to a Paul's online notes page where he has all the material I'm about to go over. But sometimes it's useful to talk through it just to make sure that our processes are sound. So the basic idea is that if you start with a function f of x, then the inverse function is the function which sends the outputs of f of x back to the inputs from which they came. So this isn't unique to trig functions. This is just the concept of an inverse function. For example, if f of 3 is 7, then that means f sends the input 3 to the output 7. Okay, then f inverse of 7 should be 3. Or if f of pi over 3 is 1/2, then f inverse of 1/2 would be pi over 3. This sort of stuff. The catch is the, how should I call this? Not function, but relation f inverse is only a function provided the original function f is 1 to 1. And we know that sine, cosine, tangent, all the trig functions are not 1 to 1. Right? If you picture the graph of sine, any horizontal line will smack that thing not just twice, but infinitely many times. So that was your horizontal line test. It fails the horizontal line test really badly. So do cosine, tangent, secant, cosecant, and cotangent. All of them are not 1 to 1. So we have to restrict their domains. So to have an inverse, we have to restrict their domains. For the sine function, whose graph looks like this, you know, and it continues on and on like this forever. We restrict the domain. Is my highlighter gone? No, here we go. We restrict the domain to just this interval. Which is negative pi over 2 to positive pi over 2. And then this piece closed on the endpoints is 1-to-1. So the domain restriction for the sine function is the closed interval negative pi over 2 to positive pi over 2. And on that interval, the sine function is 1-to-1, so we can construct his inverse. The cosine function, he looks a little bit different. We can't get away with the same domain restriction for him. He looks like this. All right, here's cosine. If I restrict him from 0 to pi, he will be 1-to-1. There are other choices we could have made, but these are the canonical choices. So if we focus just on that interval, the cosine function is 1-to-1 there. The tangent function, his graph looks like this. And it's periodic. So it's the same business over here. And this is, again, not 1-to-1, right? Fails the horizontal line test, unless you restrict from here to here. If you just take that piece is 1-to-1. So here the domain is restricted to the open interval negative pi over 2 to pi over 2. Not including the endpoints because we have vertical asymptotes there. Okay. So I've highlighted the domain restrictions in the graph. Those are the interval notation for those domains. What this means is that when I'm thinking of the inverse sine function, he's supposed to send the outputs, that's the y values, back to some x values. Since I'm restricting the domain of the sine function, the inverse sine function will only ever output numbers from negative pi over 2 to positive pi over 2. The inverse cosine function will only ever output numbers from 0 to pi, because again, those are the inputs that I'm restricting to for the original cosine function in order to make it 1 to 1. And the tangent function, I'm sorry, I didn't label these here. This is also negative pi over 2 and positive pi over 2. But I have to use the open interval because he has vertical asymptotes at negative pi over 2 and pi over 2. Are there any questions about what it is that I'm describing here? These domain restrictions? We all remember what one-to-one functions are? And can we all see that if we focus just on this piece, that this piece is 1 to 1, even though the whole function isn't? If we focus just on this piece, this is 1 to 1, even though the whole function isn't. And if we just focus on this piece, he is 1 to 1, even though the whole function is not. Okay then. So I'll leave these here, as much of them as I can. Maybe I'll cover the tangent one just for a minute so I can ask you some questions about sine and cosine. Are these randomized? Let's see. If they are, then it doesn't matter. If they aren't, yeah, they are. Okay. So can we find the inverse sine of square root 3 over 2? Let's see. So I'm looking for an output for the inverse sine function. That's going to be an input for the regular sine function. So I'm asking for what input from this interval is the sine of that input equal to root 3 over 2? In other words, what angle between negative pi over 2 and positive pi over 2 has sine root 3 over 2? Who can help me with that? Maybe useful to think about your unit circle here.
Pi over 3.
Yeah, good. So this is equal to pi over 3. Why? Because the sine of pi over 3 is root 3 over 2. How about this? How about the inverse tangent of negative 1? So for what angle between negative pi over 2 and pi over 2 is the tangent of that angle equal to negative 1?
Is
Pi over
it
4.
pi over 2 or negative? It's negative pi over 2.
It's not. No, the tangent of negative pi over 2 is undefined, right?
Negative pi over 4.
Very good. Negative pi over 4. A quick note.
Couldn't 5 pi over 4 work too? Or
Yeah, that's my note. So tangent inverse of negative 1 is not 5 pi over 4. Who can explain why?
Because it goes,
Oh, it's outside the domain.
goes clockwise.
Very good. So negative pi over 4 is right here. And here's the point negative pi over 4 comma negative 1. 5 pi over 4 is right here. So 5 pi over 4 does lead to the output negative 1, but it doesn't come from our restricted domain. If you're thinking about it in terms of the unit circle, those points are coterminal. Here's the point we're all thinking of, right? If you think about getting there by going down pi over 4, then you're good. But if you think of it by coming around like this, 5 pi over 4, then you're outside of our restricted domain. Does that make sense? Similarly, for the pi over 3 guy up here, this sign, that's why we don't choose 2 pi over 3. The sign of 2 pi over 3 over here also has output root 3 over 2, but he's not coming from the appropriate domain restriction. We need to go with that guy instead of this guy, even though they both lead to that output. Because when we decided we wanted to invert the sign function, we chose to restrict from negative pi over 2 to pi over 2. The point pi over 3, comma root 3 over 2 is right here. And the point 2 pi over 3, comma root 3 over 2 is right here. But the 2 pi over 3 input is outside of our restricted domain. Okay. So I hope that this is helping to clear out any misconceptions or things that you forgot about inverse trig functions. I'm going to give you the raw definition of the inverse trig function now. Each of them, the sine, cosine, tangent at least. And then we're going to cook up their derivatives. Are we ready for that? Are there any other questions we'd like to ask or consider about these things before we get formal about it? I know that sometimes, oh yes, go ahead.
Instead of saying negative pi over 4, could we say 7 pi over 4?
No, same issue. So 5 pi over 4 is right here, 7 pi over 4 is right here. And that would be talking about a point that's even further over. So it has to be between negative pi over 2 and pi over 2.
Okay.
This is why thinking about the graphs is every bit as important as the unit circle. The unit circle is beautiful, it's wonderful, it's great. But we must also know the graphs in order to really understand this stuff. So while these points may be coterminal, they're very different points on the graph. The circle wraps around, but the graph doesn't. So when we restrict our domain, we need to be thinking about the graph more than the unit circle. The unit circle is where we'll get the information, but we need to think about the graph to make sure we're thinking of the right angles. The correct angles, I should say. Right angles. Bad pun. All right, moving on. So the kind of raw definition of the inverse trig functions. We say sine inverse of x is equal to a if, well, let me use a theta here, because that's all what we're used to, equal to theta if sine of theta is equal to x and negative pi over 2 is less than theta is less than or equal to pi over 2. These are the definitions. We say that the inverse cosine of x is equal to theta if cos of theta equals x and 0 is less than or equal to theta is less than or equal to pi. We say the inverse tangent of x is equal to theta if the tangent of theta is equal to x and negative pi over 2 is strictly less than theta is strictly less than pi over 2. And all of the domain restriction stuff is this stuff. Since these are joined together with the word and, it's crucial if you want to get these questions right that you remember these facts. Okay. The restrictions for cosecant, cotangent, and secant are similar. So I guess we should say here, the inverse secant of x is equal to theta if the secant of theta is equal to x and 0 is less than or equal to theta is less than pi over, is less than pi. The inverse cosecant function, inverse cosecant is equal to, of x is equal to theta if the cosecant of theta is equal to x and, let me see here, negative pi over 2, let's see, 0, yeah, we got, negative pi over 2 is less than theta is less than pi over 2. And the cotangent function the inverse cotangent of x is equal to theta if the cotangent of theta is equal to x. And here we use 0 and pi again. 0, this time strictly less than theta, strictly less than pi. It's the top 3 that you'll find yourself using most of the time. So if you're worried about remembering all this stuff, focus on remembering sine, cosine, and tangent. Secant, cosecant, and cotangent, not as interesting. Secant. Yeah. Okay. So now we're ready to differentiate these things. We're going to use implicit differentiation to do it. I'm going to begin with an expression that looks like sine of something, or sine inverse of something equals y. And then I'll take the sine of both sides to rewrite it like this, and then I'll differentiate implicitly. We'll end up with an equation that we can solve for y prime, and it'll require a little bit of use of trig identities. So let's see how it goes. Derivatives of inverse trig functions. Let y equal the inverse sine of x and find, I'm going to use the prime notation because I like that more. Find y prime. But you could write it as a dy dx if you wanted. Same thing. Y equals sine inverse of x can be rewritten as sine of y equals x and negative pi over 2 is less than or equal to y is less than or equal to pi over 2. It's this piece that I'm going to play with, but I need to be mindful of this restriction. Now I apply d dx to both sides. Remember, my goal here is to hunt down and find y prime. On the right-hand side, when I differentiate, d dx of x is just 1. On the left-hand side, when I differentiate, I need to use the chain rule and differentiate implicitly. The derivative of sine is cosine, so I'll have cos y times the derivative of the inside, y prime, right? This is the implicit differentiation stuff. And now I can divide both sides by cosine of y to get y primed equals 1 over the cosine of y. And if all I cared about was finding like one tangent line, finding one point, then I could work with this. But what I really want is a formula for the derivative of the inverse sine function. I don't want it to be in terms of the variable y. I want it to be in terms of the variable x. I want to know what is d dx of the inverse sine of x. I'm going to take this relationship and make use of it. So y is the inverse sine of x. There's a bunch of ways to do this. I think the cleanest way to do this is to draw a triangle. So now, since sine y is equal to x, we can draw a triangle. X is the same as x over 1, and sine, remember, is the opposite over the hypotenuse. So my triangle, we'll draw a right triangle where the angle down here is y, and I know that the sine of y is equal to x, the opposite, so I label the opposite as x over 1, the hypotenuse. So I label the hypotenuse as 1. This side down here, I'll just call b. And we know that b squared plus x squared equals 1 squared. 1 squared is 1. So b has to be the square root of 1 minus x squared. So the cosine of y, which is what I have down here, is the adjacent over the hypotenuse, which is the square root of 1 minus x squared over 1. So my y prime, which is 1 over the cosine of y, is 1 over the square root of 1 minus x squared. And that's it. We're done. If y is the inverse sine of x, then y primed, its derivative is 1 over the square root of 1 minus x squared, i.e. the derivative d dx of the inverse sine of x is 1 over the square root of 1 minus x squared. it's a fact you'll want to know. You don't want to go through this whole procedure every time you need the inverse derivative of the sine, or the derivative of the inverse sine function. That would be a pain in the ass. I don't want to have to do all this every time I need to differentiate this function. So you want to remember this fact.
I have a question.
Yes.
So is that how you want us to do it, like the last part? Because you still get the same answer.
Well, so what I'm doing here, before today, we didn't know how to find the derivative of the inverse sine function.
Right.
This is how we discover that. But moving forward from here, I don't think you want to go through all of this every time I ask you to differentiate this function. So
Right.
I would commit this fact to memory. I would remember that the derivative of the inverse sine function is 1 over the square root of 1 minus x squared, and then not go through this every time you need it.
Okay.
But you should be comfortable with the procedure that we used here, because this procedure we could use to find lots of other things. There's nothing sacred about the sine function. Every inverse function follows a relationship like this. So if you wanted to find the derivative of the inverse tangent function, or the inverse cosine function, or the natural log, remember the natural log is defined to be the inverse of e to the x. If you want to find derivatives of any functions that are defined to be the inverse of another well-known function, you'll use something like this.
Okay.
I'm going to go through this for the tangent function, and then I'll give you the ones that you need to remember.
Gotcha.
All right. So think of this as a derivation. We're cooking up something. Any other questions on this procedure? Okay, so make sure you store this somewhere. Never forget it. Let's find the derivative of the inverse tangent function. I'll begin the same sort of way. I'll say y is equal to the inverse tangent of x means that the tangent of y is equal to x, and then I'll differentiate implicitly. I'll get out of that, I'll write it here, ddx of tan y equals ddx of x. And now the derivative of tangent y is secant squared y times y prime. And the derivative of x is 1. So y prime has to be 1 over secant squared of y. This time I can be a little bit sneaky. Instead of drawing a triangle, I can remember my Pythagorean identities. Sine squared theta plus cos squared theta equals 1, which implies that tan squared theta plus 1 equals secant squared theta. So secant squared of y is the same as tan squared of y plus 1. And what is the tangent squared of y? Well, tangent of y is x. So tan squared of y is x squared. So y primed here is 1 over x squared plus 1. That's the derivative of the inverse tangent function, i.e. d dx of the inverse tangent of x is 1 over, people usually write the 1 first, 1 plus x squared. And this is the piece here that you need to hold on to and remember. The derivative of the inverse cosine function, secant, cosecant, they all go the same way. So I'll just tell you. The derivative of the inverse cosine of x is negative 1 over the square root of 1 minus x squared. The derivative of the inverse secant function is 1 over x times the square root of x squared minus 1. And sometimes you'll see an absolute value here. But because of the domain restriction we use, you can leave off the absolute value. It's a subtle thing, and you won't need to stress about it in this class or in Calc 2. Let me think. We could cook up the derivative of the inverse, who's missing? Cosecant and cotangent. d dx of cosecant is negative 1 over x times the square root of x squared minus 1. And then the derivative of the inverse cotangent, I'll let you write for a moment. So inverse cosine, negative of inverse sine, right? The relationship here is that you take the derivative of the inverse sine function and it's just the negative. So there's this sweet relationship between the derivatives of these trig functions and their cofunctions. Derivative of inverse secant is this, derivative of inverse cosecant is the negative of this. And the cotangent function works the same way. So the derivative of the inverse cotangent function is negative 1 over 1 plus x squared. So these guys, I guess I don't need to square him, together with the ones we already had, sine and cosine, or sine and tangent, sorry. Are the derivatives of all the inverse trig functions. I don't like to ask people to memorize a bunch of stuff. I don't think that it's a worthwhile procedure to just beat things into your brain without understanding them. But I am giving you problems to work that involve derivatives of the inverse sine, cosine, and tangent functions, because those are the most commonly encountered ones. How are we doing on time? 12:31. We got about 15 minutes to play around with some examples, and that's what I'd like to do with the last bit of class here. Does anybody need more time to get these into their notes?
Yes.
Okay, I'm gonna fill up my water glass then. I'll be right back. Oh, Hamlet, you're too cute, Bubba. Oh. So let's practice making use of these a little bit, okay? Let's find y prime, where y is x times the inverse sine of x. This is going to require a product rule. I know the derivative of x, and I know the derivative of the inverse sine of x. So if I want to figure out the derivative of x times the inverse sine of x, that is a product rule thing. Y prime would be the derivative of x times sine inverse of x plus x times the derivative of sine inverse of x. The derivative of x is 1, so I get 1 times sine inverse x plus x times the derivative of sine inverse x is 1 over the square root of 1 minus x squared. So altogether here I get sine inverse x plus x over the square root of 1 minus x squared. We could find dy dx, where y is equal to the inverse tangent of x cubed. Here I need the chain rule. So dy dx is going to be, I differentiate the outer function, which is the inverse tangent function, leaving the inside alone. That would be 1 over 1 plus x cubed squared. And then I need to multiply by the derivative of the inside, which is 3x squared. And again, I could clean this up as 3x squared over 1 plus x to the 6th. So the product rule and chain rule work with these inverse trig functions the same way they do with all the other functions. Implicit differentiation also works just the same. I could find y prime where, let's say, don't want to make this too brutal. The cosine inverse of y is equal to x plus y. Here I would differentiate on both sides. On the left-hand side, the derivative of the inverse cosine of y is -1 over the square root of 1 minus y squared times y prime. The derivative of the outer function is this, and I've left the inside alone, and then I multiply by the derivative of the inner function. Same chain rule stuff, same implicit differentiation stuff we've always been doing. And then on the right-hand side, the derivative of x is 1, the derivative of y is y prime. Again, I want to solve for y prime. So I'll subtract this term over here, and then I'll be able to factor something out. I'll have -1 over the square root of 1 minus y squared times y prime minus y prime equals 1. And then I factor my y prime out, and I'll get -1 over the square root of 1 minus y squared minus 1 times y prime equals 1. And then finally, I divide over by this whole chunk to get y prime equals 1 over -1 over the square root of 1 minus y squared minus 1. So that's all. There's really not a whole lot new here. You just have a few new functions derivatives. We now know the derivative of all 6 inverse trig functions, so we can incorporate those into the problems we were doing before, whether they're product rule, chain rule, or implicit differentiation problems. We can now do those with inverse trig functions as well. Next week, we're going to start working with logarithms. We're going to talk about how to differentiate the natural log function. That's not especially hard. It follows the same sort of thing that we did to get the derivatives of the inverse trig functions. But then we're going to talk about something called related rates. And related rates are tricky. It's applications of the derivative that make this class interesting. And you guys know Isaac Newton discovered calculus by thinking about gravity and acceleration. And so those are the most natural places to apply calculus, problems in gravity and acceleration. But there's lots and lots and lots of other places you can apply calculus as well. Calculus really changed the world. The Industrial Revolution was made possible by calculus. So we're going to be looking at a handful of those classic problems, usually involving motion and time, but sometimes involving other things as well. In those problems, we will be differentiating implicitly. We will be using the chain rule. We will be using the product rule. We will be using all of this stuff. So make sure you practice and get comfy with those. If you haven't finished any of the previous homeworks, you really want to wrap those up over the weekend. Once you have those done, work as much as you can on the current homework set. I know you didn't get as much time as you should have, so it won't be due until next Friday. But we will be learning some new things starting next Monday. So the more of that you can get done over the weekend, the better. If you're having trouble with any of this stuff, please don't suffer in silence, don't suffer alone, reach out for help. I'm here, you can come to office hours or talk to me over email or Canvas messages. Also, there are tutors available at the Learning Commons. You can't see them in person because COVID is still a thing. But if you go to our website, if you go to the Learning Commons website or our Canvas course, you can follow links to get into a Zoom meeting with the tutors, and they're pretty good. Alejandro, especially, I can vouch for, is very, very good. Any questions for me before we sign out for the day?
We do have office hours today, right?
I'm sorry?
I'm saying we do have office hours today, right?
Yep.
Okay, cool.
Anything else, gang? course. Yeah, thank you guys. That's very sweet. All right, have a safe weekend. If you get stuck on any problems, don't hesitate to ask for help. If you want an immediate feedback, talk to the tutors. If you can wait a little bit, send me a Canvas message, ideally with a picture of your work, and I'll get back to you as quickly as I can. Take care, stay safe.
Thank you.